Today I want to show you how we can use laser ablation to change silicon, nice shiny wafer of silicon here, high reflectivity material because it's polished, into something we call black silicon, a low reflectivity surface that's highly structured and doesn't scatter any light back toward you. Okay, so we've got our laser ablation chamber right here, a little vacuum chamber where we can bring in some SF6 right through by the front window here. The laser will come in through the window up front. Our sample goes in here at the side. That's what we're going to do now. We're going to pull that out. We'll open up the quick flange. And you'll see a little sample holder. Very simple, this one. We'll cut out some carbon sticky tape there. That's where we're going to affix our silicon sample. We'll grab one here. Nice, shiny silicon sample. We're going to mess that up, put some laser ablation pillars on it. Stick it back in the chamber. Align it so that it's nearly vertical, facing up just a little bit. Refit the quick flange fitting. Bump it down, fill it up with some SF6, and we'll be ready to go. So there are a couple of components to our chamber. Got everything turned off now so that you can hear it more easily. But we've got a vacuum pump down here. You'll see our vacuum pump. And then it's hooked up to the chamber. The chamber itself, there's the chamber. The chamber itself is on a translation stage that allows us to move back and forth, and a second translation stage that allows us to move up and down. This translation stage we just move manually by hand, whereas the bottom one here, that's a precision translation stage that is operated with this controller here. Now, operating the laser, we got to turn it on. What you'll hear, it's very loud. Why is it loud? It needs lots of air cooling and water cooling to get rid of all the waste heat. Flash lamp pumped YAG laser is rather inefficient in creating light. So it needs a lot of cooling. You'll hear, once I turn this on, that the water pumps are going to kick in, the fans will be on, there's going to be lots of noise. We're going to start it off in a long pulse mode. That'll let us align the laser. And there's a separate Q switch mode. That's where we get the high intensity nanosecond pulses in this case. First, it just warms up a little bit. Then we can actually turn on the flash lamps. It's in the low power mode. You may hear a little bit of clicking in the background. The clicking is the electrodes on the flash lamps flashing. So the first thing we have to do is line up the laser. And you'll notice, first, we've got a beam block in the way. Want to make sure that the light's not going around the table to places we don't want it to. Then in the beam path here, we've got a dichroic mirror, 100% reflectivity. We're using 532 nanometer light. So this is 100% reflective. This is another dichroic mirror, 100% reflective. Got a couple of iris diaphragms here to define the beam path and help us cut down on any back reflections. We want to get rid of those. That's why we've got this in here as well. That's going to knock down back reflections. I got my goggles on for safety. The light's going to come through a lens that will focus it onto our sample. Right now we've got another beam block here just to make sure nothing gets to the sample until we want it to get there. Right? So right now I'm going to let the light through in this low power mode, and then we're going to line things up. Everything take a look. Crack reflections, they're where we want them to be. Sample, I've got my goggles in so I can look from the top and see if it's hitting the sample. And then we'll line everything up before coming in with the high power beam. To enhance ablation, we add some SF6. So we just need to open up the main cylinder here. The regulator is already set. And then we're just going to add a little SF6 flowing through our chamber so that we attain a steady state pressure of about 2 to 4 kilopascal. Okay, so now we've done the ablation, and let's take a look at our sample. We pump out the SF6, let everything back up to atmospheric pressure. And there you go. Now we've got a nice laser ablated sample. You can see those nice black silicon that we've made. We'll take a look at that in the SEM and you'll see the structure that actually makes this turn black.